Alright, welcome to the second of the pre-lecture videos for Lecture 41, the second to last one. That'll be on Wednesday, December 7th. And this is kind of a quick overview as to the main reasons for exceptions to the so-called octet rule, which is a rule for only like maybe 5 out of the 118 elements. So, the first one is going from an octet to the 10 to 18 tet rule, which applies to most of the periodic table. And I'm going to give an example of this by talking about the Lewis structure of sulfur dioxide, SO2. Alright, so if you were to start this, hopefully you could get at least to this point. You have a central sulfur, 2 oxygens on the side. So this will be an 18 valence electron structure. And if you want to count, you've got 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. And you've found that to minimize the formal charge, you can make one of these a double bond. You now have an octet on everything. The central sulfur atom and the 2 outside. But in this case, I arbitrarily chose the right bond to be the double bond, which means that you have to look at the equivalent resonance structure where the double bond is one on the left, but otherwise everything is the same. And the idea is that the formal charges actually aren't completely minimized on this. And what you could do, if you wanted to get rid of the formal charges, is make the formal charge on this sulfur right now is +1, because it has 5 electrons associated with it, and normally it has 6. Likewise, the formal charge on this oxygen is actually -1. And if you made both bonds double, then you actually completely eliminate all of the formal charges. So in this structure, just to review again, so the sulfur has a +1 formal charge, the singly bound oxygen has a -1 formal charge, and the doubly bound oxygen has a formal charge of 0. So if you make the second double bond, the formal charge on the sulfur is now 0, so you can attribute or assign 6 electrons to it by formal charge counting. That's what it usually has, so it's going to be 0. And likewise, you can assign 6 electrons to the oxygen. Oxygen also usually has 6 valence electrons, so that formal charge is 0. But it looks like we might have broken the octet rule on that central sulfur. By octet counting, we can assign 10 electrons to that central sulfur. But that's not a problem. Because if the valence shell is the n equals 3 shell or larger, d, and in some cases f orbitals are available, which is why the magic number goes from 8, which is the total of electrons in an s and a p subshell, to up to 18, which is the total number of electrons in an s, a p, and a d subshell. 2 plus 6 plus 10 gives you the 18. Now, the rule here, though, is be careful and do this only if the formal charge situation gets better, as it does here, and also that the central atom, or the atom that you're doing this to, is 3rd row or higher, which again is, a majority of the periodic table. So that's exception 1. Exception 2 is when you can't get to 8. So it's kind of the opposite problem. And again, I will just jump into this with an example. Boron trifluoride. So if you do the counting, the boron contributes 3 valence electrons. Each of the fluorines contributes 7, so you've got a total of 24 valence electrons. The formula strongly indicates a central boron with peripheral fluorine atoms attached to it. And then the next step in the procedure would be to put 3 unshared pairs around each of the outer atoms. And if you count at home, you will find that this is all 24 valence electrons. There is a full octet on the fluorines, but not on the boron. And to give some practice, the formal charge on these are also 0. You can assign 7 electrons to any of the fluorines. That's what fluorine usually has, so no formal charge. Likewise, you can assign 3 electrons to boron by formal charge counting. Boron usually has 3 valence electrons, so there's no formal charge there. So the octet rule is satisfied for fluorine. There's no formal charge anywhere, but boron does not have a full octet. And the issue is that if you were to put an octet onto the boron, you would need to make one of the fluorine-boron bonds a double bond. That would actually give fluorine a positive formal charge, and that is one of the 2 things I told you to never, ever, ever do. So as a result, boron, carbon, nitrogen, oxygen, and fluorine will never exceed the octet rule. But if if getting to an octet gives you a really unfavorable formal charge distribution, not hitting 8 is okay. It's fairly rare. It usually happens with boron and beryllium. Alright. Third of 3 exceptions. Sometimes some species have an odd number of electrons. Having an odd number of electrons makes a species somewhat unstable and very reactive, so you don't see it very often. But, so one example is nitrogen monoxide, and if you do the math, nitrogen contributes 5 valence electrons, oxygen 6, giving us a total of 11. So start with the Lewis structure, put 1 bond in between them, and then start putting 3 pairs of electrons around all the outside atoms, and you get to 11 before you put 3 complete pairs around there. And you just can't get this perfect without breaking the octet rule. So there's a formal charge of -1 on the oxygen in this structure, of +1 on this structure. You can reduce it by making a double bond. So in this case, the octet rule is now satisfied on the oxygen. And the formal charges are reduced as well. So there's no formal charge on the oxygen. By octet counting, it has a full octet. So the oxygen atom is actually pretty happy in this setup. The nitrogen atom at least has no formal charge, but it does not have an octet of electrons. By octet counting, you've got 7 associated with it, but if you have an odd number of electrons, you sometimes just can't do that. It's rare, but it happens. Molecules like this that have an unpaired, unshared electron are referred to as free radicals. They tend to be quite reactive. You don't run into them very often. This one, however, is important because this is a signal molecule that is used in regulating blood pressure. So the production and removal of this stuff in your bloodstream can trigger and stop vasodilation, so it makes your blood vessels larger or smaller to fine-tune the blood pressure. And for that discovery, the people that figured that out were awarded the 1998 Nobel Prize in Physiology or Medicine. Alright, so to recap, we seem to talk about 2 things when we're looking at Lewis structures, octet or formal charge. And you might ask what's more important. And the answer is it depends. So, if you're talking about a second or first row, for that matter, element, the octet rule is probably the most important thing in that you really don't want to exceed, because nature just doesn't seem to do that. You can break the octet rule for elements in the 3rd row or higher, so the valence shell is n equals 3 or higher, and as long as you can get the formal charge better in doing so. Exceeding the octet energetically has a cost associated with it, so there's got to be a payoff, and in this case the payoff is generally a reduction of the formal charge. And so we did this in our sulfur dioxide example. Now, underfilling an octet is okay, but basically that happens when there aren't electrons, or there aren't enough electrons to go around. And when taking that small number of electrons to fill an octet will give you a bad formal charge distribution, a positive fluorine is usually how this happens. So watch out for that. And don't do it. Now, the minimization of formal charge is also a nice way to figure out the best way to go for these Lewis structures. So the first thing you want to do is minimize their magnitude, and that seems to be the most important. Second, after that, minimize the number of atoms that have a formal charge on them. And the third tiebreaker, which you almost never get down to, is you want to minimize the distance between atoms that have a formal charge. But usually if you can just get them down to plus or minus 1, that's usually a win. Alright. Another thing to look out for is to put the charges on the atoms that want it. Namely, put the negative formal charge. The negative formal charge is best put on the more electronegative atom. So try to avoid positive oxygens and straight up avoid positive fluorines, and also metals with a negative formal charge, because nature doesn't do that. You can actually get a negative formal charge on metals, but you really have to work hard on it. Alright. Now the other thing is that if you want to discount some structures, be careful about using only electronegativity. Nitrogen is a pretty electronegative element. Again, it's tied for third. So putting, when deciding between having a negative formal charge on either oxygen or fluorine, either one of them are usually pretty happy with it. And we'll talk more about that in class. All right. And finally, a few words about octets. Again, don't forget about this when you're dealing with formal charges. Most structures involving carbon, nitrogen, oxygen, and fluorine almost always end up with a filled octet. So keep that in mind. Underfilling octets is actually fairly rare, and it's usually involving boron or beryllium. And again, the other usually place that you run out of options for a filled octet is if you don't have an even number of electrons. Alright, that's it, and I will see you tomorrow.